Hi, I'm going to answer several questions that you have raised. The first one is to check that Rolle's theorem applies to this given function. F of x is equal to sine of 2 pi x over the interval from -1 to 1. And we want to find all points C as described by Rolle's theorem. So quickly, what was Rolle's theorem? Rolle's theorem says that if you have a function that starts at some height and comes back to that height, somewhere in between these 2 points, its derivative has to become 0. The assumption is that the function is continuous over the whole interval and it is differentiable in between. So if it goes from one of these blue points to the other one, we are guaranteed that there are such points. In the theorem, letter C is used to indicate these, where the derivative will become 0 and tangent line will be horizontal. First of all, the function f being sine of 2 pi x is continuous everywhere. It's differentiable everywhere. We have no problem with that. What is the value of the function at the beginning and end? F of -1 is sine of -2 pi. I hope you remember from your trigonometry, sine of multiples of pi is 0. Similarly, f of 1 is equal to sine of 2 pi. That is also 0. Notice that as x ranges from -1 to 1, the argument of sine is going to change from -2 pi to 2 pi. So if you remember the graph of sine, it's going to look like this. Suppose this is -1 and this is 1, so this is 0. The argument is going to run through -2 pi to 2 pi, so it is going to go through excuse me. So each of these wave patterns from here to here is one cycle. As x goes from 0 to 1, the angle has gone through 0 to 2 pi, and we are covering the entire circle in each case. So what would be the point C? Point C will be these points. There are 4 of them. You can see their location. This is going to be at a quarter of this interval. It's a quarter, and this one is going to be 3/4, and these are going to be negative values of those numbers. Well, in this solution, we needed to know about the sine and its graph. What if we want to do it by Rolle's theorem itself? So we go ahead. So f of x is sine of 2 pi x. What's going to be the derivative? The derivative of sine of 2 pi x is 2 pi cosine of 2 pi x. Rolle's theorem says that the derivative becomes 0 somewhere between the endpoints. Here are the endpoints, is -1 and this is 1. At what points would the derivative become 0? Well, now we are back to the following question from trigonometry. Cosine of what angles is going to be 0? If you remember that, we are going to have an easy time here. Otherwise, essentially you need a review of trigonometry. Well, cosine of 90 degrees is equal to 0, and any odd multiple of 90 degrees is going to have a cosine that's equal to 0. So let's call this thing angle theta. For what angles theta are we going to have a cosine that is 0? Let's write the angle in radians. Here we are going to have y radians, because in calculus all angles are considered to be in radians, otherwise the differentiation formula would not be correct. So angle at which cosine is 0 is going to be pi half. Also the negative of this angle has the same property. Same thing at 270 degrees, which is 3 pi half, and also 5 pi halves, and so on. So if the argument of cosine becomes any of these numbers, then cosine is going to become 0. So I go ahead to set the argument 2 pi x equal to the first one of these, pi over 2. I'll divide by pi, divide by 2, and you are going to get x is equal to plus or minus 1/4. These are these two locations, minus 1/4 plus 1/4. If you say 2 pi x equal to the other angle at which cosine becomes 0, set it equal to 3 pi over 2, plus or minus of that is acceptable. X is going to be divide by pi, divide by 2, you get plus or minus 3/4. If you set 2 pi x is equal to plus or minus 5 pi over 2, that tells you that x is equal to plus or minus 5/4. Rewrite this thing again. Well, 5/4, we have already left the interval of interest. That's going to be next root that is here, but we are limiting ourselves to -1 to +1. So this one not in the given interval. So what are the candidates for C? C are these numbers, plus or minus 1/4 and plus or minus 3/4. That is the answer to this question. Okay, that was straightforward. Let's go to the next question that you guys raised, and that one is just consider the function f of x equals to x minus 2 sine of x, where x itself is limited between 0 and 3 pi. Find intervals of increase and decrease, maximum, minimum, intervals of concavity, inflection points. So essentially, if you were at a restaurant, you would say all the way to everything that needs to be done to this function to analyze it. So we want increase and decreasing interval. We want relative max and min. We want intervals of concavity up or down, and we want the inflection point. So the whole list. Again, perhaps your difficulty was with respect to dealing with trigonometric functions. A good background in trigonometry is going to be needed later on, both at the beginning of Cal 2, in differential equation, and of course in a lot of courses in engineering when you have to deal with either currents or vectors and such. Okay, what's the story here? Here are the brief review of the issues involved. increasing, decreasing function. If a derivative of a function is positive, then f is increasing. If a derivative is negative, f is decreasing. If you go from increasing to decreasing, going up and then going down, in between you are going to have a relative maximum. The other behavior, if you are going through a decreasing interval, then you follow with an increasing interval, so you're going down and then up. In between you're finding a relative minimum. Concavity up refers to a curve that is in this position. Concavity up is synonymous with second derivative being positive. Concavity down is a piece of a function that looks a function that piece of it looks a piece of this one. So this is concavity down, and the characteristic of it is that second derivative is negative. Inflection point, if you go from concavity up to concavity down, or from concavity down you go to concavity up. This one, for example, here's a concavity up, and then you go to concavity down. In between you have an inflection point. Also, if function was opening downward, then opens upward, in between it's going to have an inflection point. So these are examples of inflection points. Okay, that was a very quick review of one whole lecture. How does one go about this thing? Of course, you see that you have first derivative and second derivative. You have to find the derivatives and do a sign analysis. You have to have a clear sign table showing exactly what happens. So we go here for increasing, decreasing intervals. You have to find f prime of x. F prime is 1 minus 2 cosine of x. To figure out when it is positive or negative, we need to find the critical points. In this problem, the only critical points is where the derivative is just 0. There's no other type of critical points here. I set this thing equal to 0. That tells me cosine of x has to be equal to 1/2. Okay, so far easy. Was easy. Next is the difficulty, which is for what angles is the cosine equal to 1/2. Again, a good knowledge of trigonometry, basic trigonometry, is needed to answer this question. Let me just quickly go over some of these things. For cosine of x, if I could force every calculus student to take trigonometry before taking calculus, that would have been a major achievement, but I haven't been able to do that. So we have to do these reviews all over the place. Suppose this is say pi over 2 pi 3 pi over 2 2 pi 5 pi over 2 and then finally 3 pi. The question is posed about the interval from 0 to 3 pi. That's why I'm going on this picture from 0 to 3 pi. I'm going to limit myself to the graph of cosine of x, because that's what I need for solving this equation. Cosine starts at 1, if you remember. At 90 degrees, this is the same as 90 degrees. This is the same as 180 degrees, and so on. Let me use a different color. Say, okay, starts at 1 at 90 degrees. becomes 0. At 180 degrees it becomes -1. At 270 degrees is 0 again. At 2 pi we have come back full circle. We are at 1 again. This is -1 here. Then we go down again. At 3 pi we reach -1 one more time. This is graph of cosine of x. What do you want cosine of x to be? The y value of it is supposed to be 1/2. 1/2 is here. Okay, these are always y values. When does it become 1/2? Keep going until you hit the picture. That is just where cosine becomes 1/2. This is one location. Keep going. Here's another location. Keep going. Here's another location. Challenge is in finding these things. Well, you can use your calculator, or if you remember from trigonometry, what angle was it whose cosine was 1/2? You remember it was 60 degrees, or pi over third. So let's go right. This is pi third. So what we know or figure out from calculator is that cosine of pi third is 1/2. Now ordinary calculators wouldn't show you pi. You have to kind of negotiate with it until it tells you anything about pi, but perhaps the new breed of calculators make your life so easy it would even tell you it is pi third. So what do? You enter 1/2, you press inverse cosine, and then you get your angle. You might notice that this is pi 6. Now can you tell me where is this one? Did you figure out what angle is this one? Well, there are several ways of going about it. Either you measure this and add to that, or a method that is more standard, referred to in text, is complete the graph of cosine. Here, let's go to the other side as well. There's actually this angle in the fourth quadrant which has cosine equal to 1/2, and that is just a negative of this angle, minus pi third. If you find these two, these are called the base solutions. If you find these, then all the other solutions are easy to obtain. All that you have to do is to add 2 pi to these to go to the next category. That is from here to here. The curve is being pushed forward by 2 pi, so this is really 2 pi added to that. So if I take 2 pi and add to that my base angle, which was minus pi third, I get 5 pi third. That is where this one is. And this one, you take this angle and add 2 pi to it. You're just moving from this crest to the next one. 2 pi plus pi third, and that gets you to 7 pi third. That is where this angle is. So the angles that you were after, cosine of pi third is 1/2, cosine of 5 pi third is also 1/2, and cosine of 7 pi third is also 1/2. But perhaps if you convert all of these things to degrees, it becomes more familiar to you what is going on. But again, in calculus, all angles are done in radians. So we digressed quite a bit because we were reviewing trigonometry. Let's go back to see what was the question. we wanted to find the increasing decreasing intervals. We took the derivative, set it equal to 0, and found the solution. Here are the 3 solutions. What are we supposed to do with that? We are supposed to make a sine table. So I go ahead, make my table here. Here's the x-axis. Book says limit yourself to the interval from 0 to 3 pi, just so that we don't get carried away with all of this discussion. We had the f prime of x, which was, I forgot, f prime was 1 minus 2 cosine. Now we want to say something about the function f itself. Excuse me. We go ahead, line up all of our critical points. The critical points, the only ones we found were pi third, 5 pi third, and 7 pi third. At any of these, the derivative became 0. Now we have to go and choose some test points. So what's a good test point? To the left of pi third? 0 itself is pretty good, or you could have used anything else, any number in between. For example, if you want to use pi fourth, pi 6, any of them would be fine. What if I plug 0 in this? 1 minus 2 cosine of 0. Remember, cosine of 0 is 1. So this whole thing becomes a negative number. So in this interval, the sign will be negative. From pi third to 5 pi third, what's a good angle to use as a test point? For example, pi is good. If you take a pi and plug in this, cosine of pi, you have to remember, cosine of pi is minus 1. 1 minus 2 times minus 1 makes plus 3. That's positive. So long as these roots are single roots, our signs are going to flip-flop. Or if you wish, just go ahead, find another test point here. Like 2 pi is fine. 2 pi, cosine of 2 pi is equal to 1. You plug it here, you get negative. You go past that, perhaps you want to use 5 pi over 2 as your next test point. Cosine of that is going to be 0, and when you subtract, you get positive. So ordinarily you get a flip-flopping of the signs. The only time it doesn't happen is when these roots happen an even number of times. If this had happened twice or 4 times, signs wouldn't change. Okay, to make the discussion short, what happens to the function f? Well, here it is decreasing, over there obviously increasing, decreasing again, and increasing. So we are ready to give some answers. Intervals of decrease, obviously from 0 to 5 to pi third, then 5 pi third to 7 pi third. Intervals of increase, well, as you see, this is an interval of increase. You read it off from the x-axis. That's how we report things. Interval of increase is from pi third to 5 pi third. From here to here we are going up, and from here to here 7 pi third all the way to 3 pi we are going up. While we are here, we might also say relative max. Here's a relative max. Happens at x is equal to 5 pi third. Relative min happens at x equal to pi third, and x is equal to 7 pi third. So what does that mean? Sorry. here we have relative mean, here we have relative max, right at this point. Again we have a relative mean. If y is also requested, how do you find y? Well, you have to go back to the original function. Original function was x minus 2 sine of x. So if you want to find the y, you have to plug it here. X is just 5 pi third minus 2 times sine of 5 pi third. Okay, again, issue from trigonometry. What is this? 5 pi third, that's fine. Sine of 5 pi third, that is radical 3 over 2 times minus 2 makes this thing plus radical 3. Same way here at x equal to pi third, that's probably most familiar to you. What is y? Y is going to be x, which is pi third, minus 2 sine of pi third. Sine of pi third is radical 3 over 2. Sine of 60 degrees, radical 3 over 2 times 2 makes it minus radical 3. When x is equal to 7 pi third, again y becomes 7 pi third, and sine of that, that's still in the first quadrant. Again we get minus twice sine of that, becomes minus radical 3. So these are relative max and min. X of it 5 pi third, that's relative max. Y of it 5 pi third plus radical 3, these are relative mins. Here is one location, here's another location. Next issue, which is intervals of concavity. Intervals of concavity, we want to find that. Well, so far you remember that our function was x minus 2 sine of x. We differentiated that, became 1 minus 2 cosine of x. We need to differentiate one more round. It becomes 2 sine of x. We need to know when this second derivative positive and when it is negative. You need to remember the graph of sine of x. Sine of x, drawing it quickly. Okay, I didn't do a good job of drawing this, but 0, pi, 2 pi, here is 3 pi. Graph of sine of x is going to be positive from 0 to pi, and then again from 2 pi to 3 pi. That's where second derivative is going to be positive. That's going to make the function, original function, to be concave up. So what is our process? Our process is to set this thing equal to 0, find the roots. Who are the roots? Well, there are many roots. The ones that we want to obtain in the interval from 0 to 3 pi, they occur at 0, pi, 2 pi, 3 pi. These are really endpoints of intervals, so depending on your point of view, you could consider them as points of inflection or not. That's splitting hair over there. We go ahead, make a x-axis. Again, we are limiting ourselves to 0 to 3 pi. Sorry, again. Our points which are roots of or critical points for f double prime are at pi and 2 pi. Here is a second derivative. It becomes 0 at all of these locations, this being 2 sine of x. And our verdict about the function f, well, from 0 to pi, second derivative is positive, so function is concave up. From pi to 2 pi, sine is negative, that makes the function to be concave down. From 2 pi to 3 pi, again the function is positive, second derivative is positive, and the original function is going to be concave up. So intervals of concavity up is from 0 to pi and 2 pi to 3 pi. Intervals of concavity down is from pi to 2 pi. Inflection points, well, x equal to pi is one of them, intermediate points. X equal to 2 pi is another one. Let's just remind ourselves that I need to see the original function again. It was sine minus 2x. Let me remind ourselves. X was x, y was x minus 2 sine of x. So when x is equal to pi, y is equal to pi. Sine of pi is 0, so I don't need to do anything more here. Again, when x is 2 pi, this is 0. Y coordinate of inflection point is 2 pi. These are the two inflection points that sit inside of this interval. As you can see, that any multiple of pi is going to be inflection point if you care to extend your graph and keep going. Now it would be quite instructive if you actually sit down and try to graph this function. There are many software available that you can use to help you for graphing also. Many free software available. If you are interested, let me know and I help you to find it. Okay. Your next question was from do you want to pause this for a moment and go figure out what the graph looks like and come back? You remember we had a minimum point at 0. 0 minus 1 was a minimum point, so let me write that. Then here are two inflection points. They are also the x-intercept. The more interesting inflection point at x equal to 1 over radical 5, so almost like I have to go down by almost a half. It's slightly more than that. Okay, so here and here. So I have an inflection point here, another inflection point here, another inflection point here, another inflection point here, 4 inflection points. X squared minus 1 cubed. When x is a large positive number, let's say x is equal to 10. 10 squared 100. 100 cubed, that's going to be what? 1,000,000. by time x is 10, we are all the way up, escaping to infinity. At minus large numbers, also this function is all the way up. So when you want to graph it, it is going to be coming quickly down. Here's an inflection point. Derivative is 0, and inflection point happens at the same point. That means we are going to become flat and then cross over. Notice how I did it. We know the derivative was 0 here, and it's also an inflection point. So the inflection of the curve has to change. Also, it has to become flat because the derivative is 0 here. Then I go down. At this point, again, I have another inflection point, so I'm going to turn inflection up. Here, inflection is still up. It changes again. By the time it reaches here, it has to become flat and also have an inflection and pick up speed and go quickly up. So this is the graph of the function. At this point, you noticed I hit the minimum, so I turned around. So there were 3 locations where the derivative became 0. Here, derivative became 0 here. Tangent line was horizontal. Tangent line became horizontal here, and tangent line became horizontal here. Tangent line became horizontal and it was a minimum. Here, tangent line became horizontal and nothing of the minimum maximum type happened. We had 4 inflection points. 1, 2, 3, and 4. So that completes the analysis of this function, and so that was a good exercise. Next problem in this category, a bit more challenging, because the function that we are going to look at is not polynomial type. Let's go ahead and take a look at this function here. F of x, or it's called b of x, but let's just go ahead and call 3x to the power of 2/3 minus x. Okay, what's going to be hard here? The fact that this is not a whole number is going to create a bit of a problem. We go ahead and take a derivative. Again, the question is all the way. Do all the derivatives, analyze everything, mention everything that is valuable to say. We differentiate 3 times the exponent 2/3 x to power of, lower the exponent, becomes minus 1/3 minus the derivative of x, which is just 1. To clean this up, I get 2 over cube root of x minus 1. Maybe that's more understandable than what we had at the beginning. So I have to set my derivative equal to 0 to find critical points at which the derivative becomes 0. So what does that tell me? It tells me cube root of x, if you wish, take the 1 to the other side and cross multiply, you get cube root of x is equal to 2, which tells you what? How do you find the x? You have to cube both sides, you get x is equal to 8. That is one type of a critical point. This is a point at which the derivative is 0. Derivative at 8 is 0. Is there any point at which the derivative does not exist? If you look at this, you see that obviously at x equal to 0, f prime does not exist. So when we want to make our very first table, this table is somewhat different from the previous one in the sense that one contribution to the table comes from not from where the derivative is 0, but where the derivative doesn't exist. So here we say x-axis domain of this whole problem. It's not restricted at all. It goes all over the place. Here is f prime 2 over cube root of x minus 1, or let me make some space here. Our critical points are at 0 and 8. Okay, I'll go find some nice test points here. Here's test point 1 is a good test point. Minus 1 is a good test point. Going past 8, any number would be fine. Since I have to take cube root of it, perhaps I go all the way to say 27, but anything would do. Okay. If I take 1 and plug it here, what do I get? 2 over cube root of 1 minus 1, obviously positive. If I have negative 1 and plug it in this derivative, 2 over negative 1 minus 1, obviously I get a negative number. How about 27? 2/3 minus 1, that makes a negative number. That concludes our testing. It's good for us to remind ourselves that at 8 the derivative became 0. At 0 the derivative is infinity, plus or minus infinity. Why? Because we are dividing by 0. Now we go ahead and our final verdict about the function f itself. Derivative is negative, so I gotta be going down. Derivative positive, I'm going up. Derivative negative, I'm going down. In between here, I surely have a relative min. In between here, I surely have a relative max. Now I can harvest this table and say plenty of stuff. So I can say intervals of decrease is from minus infinity to 0, and then from 8 to infinity. Intervals of increase is from 0 to 8. Relative min happens when x is 0, which obviously remember our function was y is equal to 3 times x to the power of 2/3 minus x. So when x is 0, y is obviously 0. When x is equal to 8, what happens? 8 cube root of that is 2, square of that makes 4. 4 times 3 is 12. Minus 8 makes 4, if I'm not mistaken. Okay. Essentially, we have everything we need to get the schematics of the graph. It's coming down, going up, coming down again. But perhaps a little bit more information is going to be useful with respect to concavity. So, round 2. What is f double prime? Let's remind ourselves what was f prime, so that f prime was, I might as well write it, it was 2 over cube root of x, which now I choose to write in the exponent notation. 2 over cube root of x minus 1. This was f prime. How about f double prime? 2 was a factor, exponent was minus 1/3 x. I have to go minus 1/3, still go down one more level. Derivative of minus 1 is just 0. Combining these things is minus 2/3, x to power of minus 4/3, or minus 2 over 3 to the power of 3 times cube root of x to power of 4. Well, maybe we can be quick here. X to the power of 4 is always what? Is always positive. So this second derivative is always negative wherever it is defined. So I can say f double prime is negative wherever it is defined. What does that mean? There's a tiny problem. When x is 0, this is not even defined. Outside of that, it's always negative. Here, let me make it more formal for you if you are about to get out of your seat. Here's x axis. The only critical point of this thing is 0. From minus infinity to plus infinity, f double prime. Here it's undefined. It's actually negative infinity if you wish. Whatever number you put here as a test point becomes negative. Here you put another test point. Here again it becomes negative. Here it is undefined. It is negative infinity. What does that all mean? Well, f is concave down all the time. From minus infinity to 0, and then again from 0 to infinity. All the way here, f is concave down. Again, is concave down. How about the graph of this function? Okay, what information do we have? Bad thing about a computer is that you can't see a lot all at the same time, so we have to roll back. Here we had relative mean. I better make a correction here too. This is a relative max. Relative mean at 0, 0, relative max at 8, 4. Derivative is undefined at 0, and second derivative also undefined. So we go remember all this information, and so we had a relative minimum at 0, 0. The other one I already forgot was 8 and 4. So let's say this is 1, 2, 3, 4, 5, 6, 7, and 8. And say 1, 2, 3, and 4. This is 8 and 4. That was relative max. What was our function to begin with? Our function was we haven't talked about finding the x-intercepts. That's going to help us do a decent graph, even though it's not related to differentiation. So I'm going to do a little bit extra work on this problem to get the graph right. So I will go ahead and find x-intercepts. You remember what is that? That's where y is equal to 0. So I'm asking myself, do I hit this axis at any location, or do I hit this axis at any location? Well, 3x to the power of 2/3 minus x has to become 0 for that to happen. How do we handle this? Perhaps one way is to factor, another way is to take it to both sides of an equation and raise it to a power. And there's a certain number, many ways of doing this. Let me go ahead and factor. I factor x to the power of 2/3 out of this. I'm left with 3 minus x2. Can you guess what's going to be the power? If I extract 2/3 out of x to the power of 1, I'll be left with that. If I set this thing equal to 0, one of two things could happen. Either x is 0, which makes this to be 0, or this factor is equal to 0. If you have 3 minus x to the power of 1/3 equal to 0, that tells you x to the power of 1/3 is equal to 3. How do you get the x? You cube both sides, 3 cubed, so x becomes 27. So we have one x-intercept here, and the other intercept is way out. Unfortunately, I didn't make room for it, so let me kind of cheat a little bit here and just pretend that 27 is going to be sitting somewhere around there. So do you have everything you need to graph this function? If you remember, we said the function is decreasing from minus infinity to 0. It has to be decreasing. Let's go back here and I'll show you. The function was decreasing all the way up to 0. At 0, the derivative is undefined. It's infinity. So how is that going to show itself? This is decreasing while concave down. When it comes close to 0, its derivative is undefined. It's becoming infinity. It hits a minimum and the derivative is still undefined, so it makes a cusp. It goes back up. Now the derivative is supposed to be positive, so we go up, positive. Remember, it's always the second derivative is negative. It has to be always concave down, so it always stays like that. It comes to relative maximum at 8 and 4. Then it starts to descend. There's a relative maximum, it keeps going down. It always stays concave down. We know that it's going to hit the x-axis at 27 and keep going. I pull this 27 a bit inside so that we can finish up this problem and not to redraw again. So it goes kind of like that, perhaps not bent as much, so the scale is not quite correct. It really has to go rather slowly. It goes this way and hits way out and goes down. That's the graph of the function. I shouldn't leave a wrong impression here that this thing is not planning to turn down, so here is a correction. Keeps pointing downward. Correct that. Maybe we had enough. Okay, let's go ahead, and that is the end of this problem. You had one more question. Let me see if I can quickly answer that. This perhaps became one of the longest problem 48. Here's a question. Make room. Here's a question. Find the limit of one over logarithm of x minus 1 over x minus 1 as x approaches 1. We want to find this. This falls under category of applications of differentiation and Lopital'S rule. So we want to apply I hope you read the historical note about this person, Lopital. He actually bought the right to this formula or theorem from somebody who was much better, and that was Mr. Bernoulli. At any rate, we are just going to go ahead and apply, not minding whose name is attached to this. What is at stake here? When x becomes 1, you have to remember logarithm of 1 is 0. So 1 over logarithm of 1 becomes 1 over 0. We're talking symbolically, that's going to be infinity. Similarly, 1 over 1 minus 1 also going to be 1 over 0, and that's going to be infinity. So symbolically speaking, that is infinity minus infinity, one of the ambiguous forms. Who's going to overcome the other one? What would be the difference? A finite number or again another infinity? All sorts of things can happen, and the only way to resolve that ambiguity is going back here and taking the limit. L'Hopital says, well, if you had a 0 over 0 ratio at the limit, you can go ahead, take a derivative of numerator and denominator and resolve the ambiguity like that. Or if you had infinity over infinity, you can apply L'Hopital's rule. But if it is infinity minus infinity, first you have to convert it either to this form or that form before you can actually apply L'Hopital's rule. In this case, our process will be easy. All we need to do is going to be to take a common denominator. So I take a common denominator, x minus 1 times logarithm of x. I have to multiply this by the denominator of the first one, and second one by the denominator of the first, and take this limit. Same thing. If the limit exists, the same as that. Now when x approaches 1, this is 0, this is 0, this is 0, this is 0, everything 0, and we are dealing with a 0 over 0 case. We can apply L'Hopital rule. So I go apply L'Hopital. So by L'Hopital rule, I can, if this limit exists, I'll be done. Which limit is that? Take a derivative of that. I'll be a bit fast. Derivative of x is 1. Derivative of 1 is 0. Derivative of logarithm of x is 1 over x. Here I have to work harder. Derivative of first times second. Remember, here we have a product rule. Derivative of first times second, that is logarithm of x. First times the derivative of the second, derivative of logarithm of x, is 1 over x. One step more. I go here is equal to a limit of, we don't have to stick to L'Hopital all the time. Sometimes it's smarter to clean up before you apply one more round. So what I do is that I multiply these things by x. That is, I take a common denominator and clean up. Otherwise, I'm going to be, well, actually, I take it back. If you don't, So let me okay, on the second thought, maybe I just don't do anything here, just proceed and apply L'Hopital's rule. Just remember that you have the option, if you wish, to multiply these fractions and simplify them if you want, but now I just at this step I'm not applying L'Hopital's rule, I'm just cleaning up a bit. It's 1 minus 1 over x, I didn't do anything to that. Logarithm of x, I didn't do anything to that. To simplify my differentiation, so x times 1 over x is just 1, minus 1 times 1 over x, that's just 1 over x. So this is just a copy of that. Now I apply L'Hopital's rule again. Why can I apply it? Because when x becomes 1, this is all 0, 0, 0. Again, I have 0 over 0. I haven't resolved this thing yet. I'm going to apply one more round. Derivative of 1 is 0, derivative of minus 1 over x. What is that? That's 1 over x squared. Derivative of logarithm of x is 1 over x. Derivative of minus 1 over x is 1 over x squared. Now remember, x is approaching 1. And x approaching 1, this is no longer ambiguous. This is just 1. 1 plus 1 makes a half. And that is our answer. So limit of this expression is a half, meaning these two infinities differ. These two infinities differ from each other by half. That's quite interesting to know that they were fighting over just 0.5. Okay, I guess I had enough calculus for today. I hope you practice a few of these questions for your test.